This video is about the new way of doing temperature conversions since version 5.1. You see there, this is version 5.1. We're going to convert temperature difference in degrees Celsius to Kelvin. There you see T for temperature equals Kelvin, and then we have T equals 100 degrees Celsius. Remember, this is not temperature as scale, this is temperature differences we're talking about here. So it's a relative conversion. Okay, let's do it. Hit the evaluate, and we got 100 Kelvin. So basically 100 degrees Celsius is exactly, as temperature difference, exactly equal to 100 degrees Kelvin. So I'm going to stop the video now, or pause it. Here we're going to convert temperature scale in degrees Celsius. So that is now absolute temperature to Kelvin as an absolute temperature. You would see I've added this O degrees C here for for the 0 degrees Celsius of the scale, and then I've relatively add 100 degrees C to get to the boil point of water. So this together forms a boil point of water basically, and it should be that temperature 373.15 Kelvin. That is actually 100 degrees Celsius, and I've added the 0 degree of that is actually a O. That's O dash C of, or the 0 point of the degree Celsius scale. So that is at 0 point of the degree Celsius scale plus 100 degrees Celsius for the relatively, and then you get the absolute temperature of 373.15 Kelvin from the thermodynamic 0 of temperature. Okay, so that solves that problem. Here we're going to solve temperature difference in degrees Celsius. That's 100 degrees Celsius to Rankine. That RA is for Rankine, and I just want to show you this, converting temperature differences as 100 degrees Celsius relatively to Rankine. T equals Rankine, T equals 100 degrees Celsius. We heat evaluate, we get 180 Rankine. Okay, stop it. Here we convert temperature difference in degrees Fahrenheit to Rankine. This temperature difference, remember. So T equals RA for Rankine. T equals 100 degrees Fahrenheit. It should be the same value. Okay. In this example, we're converting temperature scale in degrees Celsius to Rankine. T equals Rankine, that will be a temperature now, and T equals the 0 of degrees Celsius, or O dash C, that's a constant, plus 100 degrees Fahrenheit. Okay, sorry, there's a mistake there. That should be an F. Okay, so that's a 0 of degrees Fahrenheit, sorry, to 100 degrees Fahrenheit plus 100 degrees Fahrenheit. So that will be exactly the temperature of 100 degrees Fahrenheit now in terms of Rankine. And there you have it. Okay, redoing the last one correctly, converting temperature scale in degrees Fahrenheit to Rankine. We have T equals Rankine, T equals a 0 of degrees Fahrenheit. That's a constant plus 100 degrees Fahrenheit, and we get that. Converting temperature difference in degrees Celsius to Rankine. T is Rankine, T is 100 degrees Celsius. Evaluate. I think I've shown this one, but I've just decided to redo it again. Okay. In this case, we're going to convert temperature scale in degrees Celsius to Rankine. You see, I've added that O-C or 0 degrees C for the 0 point of Celsius, and then relatively I've added 100 degrees Celsius, and we get 671.67 Rankine. That is a boil point of water. Here we convert temperature difference in degrees Celsius to temperature difference in degrees Fahrenheit. Now you see T is degrees Fahrenheit, T equals 100 degrees Celsius relative, and we convert it. So that's exactly 180 degrees Fahrenheit. In this case, we convert temperature scale in degrees Celsius to temperature difference in degrees Fahrenheit. Okay, T equals degrees Fahrenheit, T equals O-C plus 100 degrees Celsius, and that is your scale value for 100 degrees Celsius as temperature. That is relative, and we convert. Here we converting the temperature scale in degrees Celsius to the temperature scale in degrees Fahrenheit. Remember the scale in degrees Fahrenheit. So we have our scale in degrees Celsius, that is 0-C of O-C plus 100 degrees Celsius, that is our relative temperature in degrees Celsius, but then we deduct the 0 of degrees Fahrenheit to get the scale conversion to in terms of the multiplication factor to degrees Fahrenheit. You see, T equals degrees Fahrenheit equals 0 degrees Celsius plus 100 degrees C. You can put this in parentheses if you like. Let's put parentheses there, and then you understand the concept better. So that is my temperature in degrees Celsius. I deduct the 0 degrees Fahrenheit to convert it in terms of the scale in degrees Fahrenheit. And there's your answer, 212 degrees Fahrenheit. And we all know that is a boiling point of water in degrees Fahrenheit. That is a boil point in degrees Fahrenheit. Okay. Then we're going to convert the same, but we're going to convert degrees Fahrenheit to degrees Celsius as scale. Let's first do this one. We convert temperature scale in degrees Fahrenheit to temperature difference in degrees Celsius. So T equals degrees Celsius, T equals O-F or the 0 degrees Fahrenheit plus 212 degrees Fahrenheit. We know that is 100 degrees Celsius basically, and we should get an answer of 100 degrees. Remember, this is relative temperature, scale to relative, so that is 373.15 degrees Celsius. That is correct. We've converted 0 degrees Fahrenheit plus 212 degrees Fahrenheit to temperature difference, and gives a temperature difference of 373.15 Celsius. And that is, if it was Kelvin, because degrees Celsius is relatively the same than Kelvin, that would be the boil point of water, so that is correct. So in relative degrees Celsius, 373.15 degrees Celsius is correct. If that was Kelvin, because Kelvin and Celsius has the same size, and Rankine and degrees Fahrenheit has the same size or same relative size. It's just a zeros, that's 0. O-F and O-C, that makes a difference between Fahrenheit and Rankine, and O-C is a 0 Celsius, and obviously Kelvin has the same size. Okay, so that's that one. Here we can convert the temperature scale in degrees Fahrenheit to the temperature scale in degrees Celsius. And the answer should be 100 degrees Celsius, because 212 degrees Fahrenheit is 100 degrees Celsius in temperature scale. So let's see. You see, that's correct. I'm going to put that in parentheses just for clarity. So basically, that is your temperature in degrees Fahrenheit per scale. That is 212 degrees Fahrenheit per scale. You deduct the degrees Celsius to get it to scale to convert to degrees Celsius. And it should give the same answer, obviously. You see, so that's about it. And you can play around with this O-F and O-C if you convert relatively or absolutely between degrees Celsius and Fahrenheit. That is normally a temperature that is absolute. If you include the 0, you can play around with these zeros, O-C and O-F. Remember, temperatures in Kelvin is from the thermodynamic 0. Okay, both Kelvin and Rankine start at the thermodynamic 0, and degrees Fahrenheit start at this 0, and then you relatively add it. That's a new way I do it. And temperature in degrees Celsius start at this 0, and you relatively add your degrees Celsius if you want to create a temperature, say in Kelvin. Basically, I prefer people to work in temperatures to enter. You can enter in degrees Celsius, but if you calculate with temperatures, try to stay with Kelvin. It's just better practice because Kelvin is the SI unit of temperature. Okay, I'm going to stop it here. In this modeling, let me just get there. Must get to P2. We're going to convert. We want P2 in atmospheres. The answer should be 1, because we are asking this modeling to convert to pressure the temperature T2. Let's highlight it. Of the temperature, it's now per scale. It's O-C, that's a 0 degrees Celsius plus 100 degrees. Sorry, that should be Celsius. 100 degrees Celsius. C. Why doesn't it make a C there? My keyboard seems to be faulty. 100 degrees Celsius in temperature. So T2 is now the temperature of 100 degrees Celsius per scale. That's not relative, that's absolute temperature of 100 degrees Celsius. We're going to try to determine the boil point pressure in atmospheres of P2 using this formula and modeling. Okay, so that's the solution there, and I'm going to drop it down and you can study it. You see, that's solved it here. P2 equals that formula equals 1 atmosphere, and it confirms that that is 273.15 Kelvin, that is 100 degrees Celsius. I'm going to do the same in Fahrenheit, also at boil point of water under normal atmospheric pressure. You see that is normal atmospheric pressure. So that is not much of a calculation, but we were going to do it with 200 degrees Celsius also and see how the pressure increases. Okay, so that's that. Study it, or let me put it there, and you can study it. Okay, let's stop it there. Okay, let's highlight that. Let's get there. Okay, here we're going to do T2 in 0 degrees Fahrenheit plus 212 degrees Fahrenheit. That is also the boil point of water. So this is the same, but just in degrees Fahrenheit. And I ask P2 in terms of atmosphere, the answer should be 1 atmosphere. Because that's a normal boil point of water. So that's O deg F, or for the 0 degrees Fahrenheit plus 212 degrees Fahrenheit relatively is 100 degrees C, basically 370. You will see the Kelvin value. That's a boil point of water. We evaluate the 373.15 Kelvin. Drop down to see the report. I should evaluate the whole thing. Evaluate whole thing, and there you get the solution. So the answer is again 1 atmosphere, and the temperature is 373.15 Kelvin, boil point of water basically. But you see there as O deg F plus 212 degrees Fahrenheit gives the same temperature. So that gives that pressure of 1 atmosphere for P2. And yeah, you can study it. Okay, I'm going to pause it now. Okay, let's get there. For P2. Okay, that's the formulas. How do you get that? P2 and T2. Okay, so T2 now is 0 degrees Celsius for the scale, O deg C, plus 200 degrees Celsius. So I want to know how many atmospheres is needed so that water will boil at 200 degrees Celsius. So I want to calculate P2. How many atmosphere? That ATM is atmosphere. So I've increased the temperature to 200 degrees Celsius. That's 100 degrees over boil point. And I want to know the pressure needed for water to boil at that temperature. You can ask it another way around. It will also work. This modeling is bidirectional, so you can enter a pressure here and then it will calculate T2 in terms of whatever way you want it, whatever temperature unit you prefer. Normally it's Kelvin, but we just this is very good way of inputting a temperature by using this O deg C and O deg F, and then the relative temperature. And then you can, in this case, we're going to calculate P2, and we're going to give you the solution just now. There we go. That's just solved the problem. You see, that T2 is 473.15 Kelvin. That is O deg C plus, that's a 0 degrees Celsius. If it's F, it's at the 0 degrees Fahrenheit. Plus a relative temperature of 200 degrees Celsius above the 0. So that is boil point plus 100 degrees Celsius. And that gives a temperature of 473.15 Kelvin. And the P2 gets calculated. And it gives an answer of 15.9448 atmospheres that is needed for water to boil at 200 degrees Celsius. And we just confirmed the temperature T2 is calculated. If we had P1 at P2, it would be able to calculate T2 from the pressure. So if I would actually delete T2, I keep P2 and I delete the temperature. So I keep P2 and I delete the temperature. You will get that same temperature back. Let's try that. So we're going to keep P2 We're going to delete this temperature, and we want to see if we get that same 473.15 Kelvin. P2 we have down here. It is that amount of atmospheres. So we put it in there, cut it there, and we insert it there. We're going to do it the other way around. Paste. So we give the pressure P2, and we want to know the temperature of the at T2 at which the water will boil. If we have 15.944 whatever atmospheres, and we know the answer should be, let's just check P2 and T2. T2 T2 has now been deleted, and P2 I've given, and T2 should now be calculated, and you will see the answer. Just select everything, and you will get that temperature of 473.15 Kelvin back. And we can convert it to degrees Celsius if we like. You basically just work with the zeros and just change the unit of T to degrees Celsius and subtract the but you must play with the formula and subtract the 0, and there you have your solution. You see, now we've given it we don't worry about P1 and T1, that is calibration values. So P2 we've given as 15.94 whatever atmospheres, and then it calculates T2 as 200 degrees Celsius basically. That is 200 degrees Celsius, because 0 degrees Celsius is 273.15 Kelvin plus 200 is at 473.15 Kelvin, so that's correct. So water under about 15, nearly 16 atmospheres will boil at 200 degrees Celsius. Okay, let's clear that one. Okay, here we're going to tile some floors. We have a tile area. Let's use this buttons. Just want to get back to the beginning. We have a tile area of 20 centimeters times 30 centimeters. So that's your length, width, and that's your length of the tile. That gives you an area of 20 centimeter by 30 centimeter. You don't actually have to calculate it. The parser will do it for you. Then I use that button to go to the next expression. Then we have a floor area of 4 meters by 6 meters plus a little floor adjacent to it of 1 meter by 1.5 meter. And we want to calculate the number of tiles we will need to tile that floor. So the number of tiles is obviously equal to the floor area divided by the tile area. I've selected the values now that it divides in equally in a whole number. But you can get fractions, and then obviously you need to figure out how the tiles will be cut, and you probably would need to add a few more tiles. But let's keep it to round values. So the number of tiles is equal to your floor area divided by your tile area. We assume the tiles will fit in, so this value should fit in the tiles. So the floor area, the tile area is 20 centimeter by 30 centimeter, and the floor area is 4 meter by 6 meters, plus another area of 1 meter by 1.5 meter. And let's see what we get. Let's highlight the formulas, and there's a solution. We will need 425 tiles. You can see it there and there. The number of tiles is 425, and there's a solution. And there's a evaluated source expressions, and there's a calculation. Okay. Let's pause it there. Okay, we're going to do electrical calculation. We have three resistors, R1, R2, and R3. And we have a battery of 12 volt. So R1 equals 600 ohm, R2 equals 1.2 kilo ohm, and R3 is equal to R2. Then we calculate Rp is R1 in parallel with R2 in parallel with R3, and our current through the parallel resistors, if we have a 12 volt supply here, is Ip, that's a parallel current through the whole set of parallel resistors, is 12 volt divided by Rp. Let's see what we get. We hit evaluate, and there's your solution. Ip is equal to 40 milliamp. There you can see it. Ip is 12 volt over Rp is equal to 40 milliamp. Let's drop it down so you can see the complete solution. Pause it and study it. In this case, we have three resistors in parallel. We know the parallel resistance Rp is 600 ohm. We also know R1 is 600 ohm and R3 is 1.2 kilo ohm. But we don't know R2, so we have to calculate it. So basically R2 is a parallel resistance Rp, and then you subtract the parallel sum of R1 and R2. So Rp parallel subtract the parallel sum of R1 plus R2, that 2 you put in parallel, and you subtract it from the total parallel resistance Rp to get the value of R2, and here it goes. And we've known from the previous example, R2 should also be 1.2 kilo ohm, the same as R3. So the calculation R2 is Rp parallel subtract R1 in parallel of R3 is correct. It gives a correct answer, and there's a solution. Pause it and study it. Okay, I'm going to stop it now. Okay, in this example, we want to get the current drawn by a 60 watt light bulb of a standard 230 volt supply. That is a supply voltage here in South Africa. It's 230 volt to 20 to 30 volt 50 hertz. So that is our standard AC supply. So we have a P light with a power rating of 60 W, and that's 60 watt. V supply is 250 volt. I supply is unknown, and so we want to calculate it. We basically take the power of the light, the P light, and we divide it by the V supply, and there we evaluate it, and we get an answer of 260.869 whatever milliampere. So that is V supply. I supply is 260.8. That is the unknown that we wanted to solve. So that light bulb will draw about 261 milliampere of a 230 supply. That's a 60 watt, and there's a solution if you want to see it in the report form. Okay, so that's that one. In this case, we're going to calculate the resonant frequency of an LC circuit. Now, we normally denote resonant frequency with FO. So we have, let's get to the beginning. We have a L or a conductor, inductor, a L value of 1 millihenry. We have a C or capacitance value of 2.7 microfarad. And we have two alternative ways that actually means the same to calculate FO. So L is 1 millihenry, C is 4.7 microfarad, FO is 1 over, in parentheses, 2 pi times the square root of L times C. And if you say 1 over something, you can also, in that second case, you leave that 1 over out there and you replace it with to the power of -1. That means exactly the same. So let's evaluate this example. We select and we evaluate, and there's a solution for LC circuit. You will see the parser actually knows that FO should be frequency. We haven't stated any hertz here, but they're only giving it L value and a C value. L is 1 millihenry and C is 4.7 microfarad, and FO is a formula, and then FO is another form of the same formula. And you will see that in both cases it gets the same answer, but it actually will tell you it is in kilohertz. So you see that that's the same answer for the two forms of getting FO. So FO is 1 over 2 pi times the square root of L times C, or 2 pi times the square root of LC, all to the power of -1. And you will see the answer is in kilohertz. So that's quite smart of the parser. It actually calculates the units as kilohertz of the answer. So that's a very smart answer. No normal calculator can do that for you. It will give the answer, but it won't give you the units. So so if you click on FO there, you would see, if I select the value side, that's a whole value, on the right hand side, that these of the equation, then I get 2.3215 whatever kilohertz. You see that kilohertz there? That's FO. So I can select the full statement there, and the FO is 2 point whatever, and that's the formula is given to you. So that is a full solution to get a resonance frequency of an LC circuit. Interesting powers this parser have, and it does it in no time. You just have to set up the formula and the variables. Remember, if you use a value straight in a formula without using a variable, say you want to use that 4.7 microfarad straight into that formula in the place of C, you best put that value, the entire value 4.7 microfarad, in parentheses, because due to the PEMDAS rules, it's just better if it's a single value to put it in parentheses to ensure that that value is evaluated as a single value, and you don't get problems with the PEMDAS or BOTMAS, rules of operator precedence. So if you use a value straight into formulas, always put a value like 1 millihenry or 1 meter per second, or any value, or a variable, any value that is supposed to be a single value. Always put it in parentheses if you would replace that variables with the straight values. So for instance, you can put that 1 millihenry in the place of L in parentheses, and that 4.7 microfarad in the place of C in parentheses, and it will also give you this answer of 2.3215 kilohertz. Whatever, that is not so important. So the answer is 2.321 kilohertz, depending how precise you want the answer. You can ignore those later on digits. Okay, I hope that is very insightful.